The next part of this lecture is characteristic of an instrument. We want to be aware about the characteristics of instrument performance, and also characteristics of instrument performance are usually divided into two classes on the basis of the frequency of the input. The first one is the static characteristics, and the second one is the dynamic characteristics. The static characteristics describe the performance of the instruments for DC or very low frequency inputs. For example, when we are recording a temperature of a human body, we should evaluate the static characteristics of that measuring. What dynamic characteristics require the use of differential and or integral equation to describe the quality of the measurements, because we have some higher frequencies in our signals and we cannot use static characteristics to describe the performance of the instruments. The static characteristics included some criteria such as accuracy, precision, resolution, repeatability or reproducibility, statistical control, static sensitivity, zero drift, sensitivity drift, linearity, input range, input impedance. And we will discuss about all of these criteria in the next slides. Here, and a mean value of this distribution. Variance and mean value. The difference between the reference value of the measurements and the mean value called accuracy, and the inverse of the variance, 1 divided by variance, is the precision. For example, we want to measure that weight. We mentioned before, we have a man with 80 kilograms, and we measure in plenty of repeats. For example, 79.1, 79.2, 79.3, 0.7, 80.1, 80.8, many measurements. And the mean value of these measurements, for example, thousands of measurements, the difference between the mean value of these measurements and the reference value is 80 kilograms. We call it accuracy. And the variance of those measurements determine the precision. If the variance of the recordings is low, the precision is high. It means that the measurement is precise. We can use a well-known example of some shooters. We have 4 shooters. Shooters number 1, shooter number 2, shooter number 3, and shooter number 4. As you can see, they shoots to a target. The first one shoots to a center of the target with high accuracy. High accuracy means that the mean value of the position of the results is close to the reference center of the target. And also, high precision means that the results are not scattered on the target, are close together. These are close together. Shooter number 2 have good precision because the results are close together. As you can see, the results are close together. But the mean value, the mean location of the results are far from the center of the target. It means that the accuracy is low. The shooter number 3 have high accuracy because the mean value of these results are close to the center of the target. But the results are scattered from the center. It means that the precision is low because the variance of the results are high, and as I mentioned before, the precision is the reverse value of the variance. Therefore, when the variance is high, the precision will be zero, will be low. And the shooter number 4 is bad in accuracy and also in precision because the mean of the results are far from the center, and also the variance of the results is high. The results are scattered. And when we want to sort the shooters, the first um, the first the best I prefer to use this word. The best shooter is the first one. This is the best because also the high accuracy and the high precision of the results we can see. The second place goes to shooter number 2 because the shooter tries good, tries well. The results are good. They are close together, but we have some maybe instrumental problem. The shooter wants to hit this point and all of the results have been heated to that bad point with some distance from the center. Therefore, we have two ways to solve this problem. The simple way is change the target from the center of the target to this center. If the shooter shoots all the bullets to this point, to this new point, all the results will be hit on the center of the target. This is the first simple way. We can calibrate the output. This is the simple way. And the second one, we have some calibration problem in our devices, in our instrumental parts of our gun, and therefore we can calibrate those instrumental and solve the accuracy problem. And after that calibration, we have a good instrument in the point of view of accuracy. Also, we have good high precision. The second place goes to the third shooter, and the worst one is the fourth. Therefore, if I ask you which one is the best, you should tell me the best one is the first one. And the second, if I ask you about the position of the second and the third shooter, you should choose the second one based on the instrumental point of view, because we want to have a reliable system. We can calibrate the second one, but we cannot calibrate the third system. The third system has good mean value, but we cannot correct it. We don't have any way to solve the problem of the third one. The next important characteristic is resolution. The smallest incremental quantity that can be measured with certainty is resolution. All the words in this sentence is important. The smallest incremental can be measured with certainty. Suppose that we have a mercury temperature meter, thermometer, okay? Three, 35, 36, 37, 38. If our thermometer only have these numbers, these gates, we can only say the temperature is higher than 37, not more. But if we have another data, we have more data, we can detect that the temperature is lower than 37.5. And if we have some other bars here, now we can read the number with certainty. Certainty means that now we can see the temperature is 37 point maybe 3. Therefore, the resolution of the temperature from the beginning of this slide was improved by adding some other data, some other bars, some other facilities. And the resolution of the system was improved also, because we can measure the smallest incremental quantity with certainty, with more bars, with more data. The next characteristic is reproducibility. That means that the ability of an instrument to give the same output for equal inputs applied over some period of time. And also we can use repeatability. We have a device and we use it, for example, in the morning, at the evening, at the night, here, there, in Iran, in Iraq, in Turkey, in other countries, and the data should be the output data, the output results should be equal from the same input. Another characteristic is linearity. A system or element is linear if it has properties such that if y1, this is y1, is the response to x1 and y2 is the response to x2, then y1 plus y2 is the response to x1 plus x2, and if we multiply a k, a coefficient k, y1 should be the response to k x1. These two requirements for the system linearity are restated in this figure. And also in this figure, we should have some correction here. This is x2, x1 plus x2. Sensitivity is another important static characteristic. The sensitivity is the ratio of the incremental output quantity to the incremental input quantity under static conditions within the operating range of the instrument. All these words are important. The incremental input, the incremental output, static conditions when we vary the xd as the input parameter, other impressive parameters should be fixed, and we should only we should only have the output change based on the xd as the input parameter, input quantity. And the ratio, the slope of the interpolated line, interpolated equation, linear equation, is the sensitivity. Suppose that we have two scales to measure weights. A scale for jewelry measuring, jewelry weight measuring, and another for human body weight measuring, and another for vehicle weight measuring. We have some similar sensor in these instruments, but the sensitivity of jewelry measuring scale is higher than other types of scales. It means that the slope of that instrument is high. The slope you can see here, delta y, delta x, and the slope here is more than the main curve. And in this plot, the slope delta y over delta x m1 is smaller than m and m2. m1 smaller than m, and m is smaller than m2. Higher slope, higher sensitivity, and smaller slope, lower sensitivity, small sensitivity. We call this curve also, I emphasize that we call this curve calibration curve of a measuring instrument. We can plot this calibration based on some experiments, based on some tries, and after that we can measure the slope of that curve to calculate the sensitivity. And in some situation, the sensitivity will drift. As you can see, the sensitivity can based on because of some problems or some changing, some varying of some situation can be changed, and we call that sensitivity drift. If the slope of a curve increase, we have a plus sensitivity drift. If the slope decrease, we have a negative sensitivity drift. Also, in a calibration curve, because of some problems, zero drift will be occur. As you can see, we have some zero drift. The changing of the intercept value, the difference between 0 and the point here, point on xd0, we called it intercept V. The difference between this value and the varying intercept value is zero drift.